good day. I'm Dr. Sabri. I'm going to teach you on the chemical reaction engineering for the subject of Introduction to Chemical Engineering. The objective of the third lecture is I'm going to cover the energy balance of the reactor and how the energy balance and how the problem with the undesired reactions. You must be able on how to explain how the energy balance is determined and how problems with undesired reactions are managed. As you have learned before in the second lecture, these are a summary of mole balance reactor. General mole balance actually comes from this drawing. It has flow of inlet and flow of outlet. Fj0 is actually the flow rate of J into the system. Fj is minus Fj is flow out of the system. Tj is the rate of generation by chemical reaction within the system. The NJDT is actually the rate of accumulation within the system. So as wrote before, this equation such as the term before and in the left side will be the variable or the term telling you what is happening in the system, whereas in the right side will be the summary of J concentration or J molar or number of mole. Knowing that delta G is Rj delta V, so we can get ODE or differential form for three reactors like batch reactor, PFR and PBR. Okay, and when we change the temperature, this is isothermal reactor. This is for isothermal reactor where the temperature is not changed. At the constant temperature, T here is same as T1. So the rate constant will not change with the temperature because temperature is fixed. But when temperature is no longer fixed, the reaction will change according to temperature. So as you can see here, this is more balance of plug flow reactor. And inside the more balance of the plug flow reactor, you can see here it is rate law. And if we have this rate law, the rate law is initially comes from negative K Ca. Example that the rate law is this for A to form B, right? A to form B. So the K is actually calculated from Van Hoff equation. Sorry, from Arrhenius equation, not from the Van Hoff. Arrhenius equation. Inside the Arrhenius equation, it will have T initial and then T at the outlet of the reactor. K will change with temperature, and Ca we write in the form of conversion. So this is actually equation in conversion. Conversion is actually Fa0 minus Fa per Fa0. So when we it's come from dFA dV equals to Ra. So Ra. So when we have this into general mole balance of the mole balance of the plug flow reactor. So that's why you can get this equation. And CA is calculated from the conversion like this, and finally you can get the equation of mole balance with the third variable. So this is one variable, first and second variable, and the third variable will be the temperature. So in order to determine the design variable for the plug flow reactor, this for plug flow reactor, you need to determine T, you need to determine T and V. Sorry, your design variable is not only V, it's also T. So we need to have another equation which is energy balance. For adiabatic reaction, the energy balance can be written as this, where the heat capacity is constant. So by having this equation, then you can have a graph have a table, set X, and then by using energy balance equation, you can find what is T. From the T, you can use Arrhenius equation to calculate K. From the K, then you can calculate using the rate law, negative RA, and then from negative RA, then you can calculate FA0 for negative RA, and then you can repeat again for the next value. Let's say from in the beginning it is 0, and then 0.1 until 0.95. Then you can plot graph like this, and the volume will be area under the curve. How to find it? We normally use trapezoidal rule. We draw some lines here, then we calculate segment by segment using trapezium area formula, trapezoidal rule, or how we calculate trapezium area. So that is the way we calculate the area under the curve. This is the way on how to determine V for PFR. And at the same time, T change with the reaction. This is for adiabatic, where the temperature is changed with the reaction. Adiabatic means there is no Q dot 0. That means the reaction is fully insulated with it is isolated. There is no heat transfer through the wall of the reactor. So for the adiabatic reactor, the temperature only change due to the reaction. In this case, the temperature will increase, and because of the exothermic reaction, and the plot will be like this. From the area under the graph, we can find out what is the volume of the reactor. That is the way we determine the design variable for non-isothermal reactor. What is the use of energy balance? We normally use energy balance equation to get high selectivity and yield and conversion, to avoid runaway reaction, to avoid deterioration of chemicals, particularly biochemical, and finally to optimize the heating and reduce the cost. One example, this common phenomena for reaction. If you increase the temperature, the conversion will increase. Sometimes you will have runaway reaction, where the second undesired reaction can appear. Normally it is combustion. This normally happen in partial oxidation reaction. It will also have another reaction that will consume or burn or oxidize completely the reactant. So it will have trend like this. After certain temperature, the conversion will be shooting up to almost 100%. Normally it will go like this. The selectivity normally decrease with the temperature because of the side reaction. Similarly to the yield also decrease with the increase of the temperature. So in reaction engineering, we got to fine tune between conversion and the yield because of this phenomena. So this is simple structure of temperature controller for a reactor. So this is CSTR drawing for the CSTR. Okay, so this illustrate how the temperature is controlled in order to get optimum temperature and optimum temperature for the operation. Next, what will happen if we have more than one reaction in the reactor? Normally, the second or third reaction will be undesired and can consume the reactant or the product that is used in the reactor. The purpose of the design in multiple reactions is to maximize the selectivity, yield, and conversion. Plus, with the previous one, which is controlling the temperature, the undesired reaction will complicate the control and will make attempt of maximizing the selectivity and yield and conversion become more difficult. There are three types of reactions or multiple reactions, which are first is series A to form B and C, B to form C. That second reaction that will consume the product to form undesired product. Parallel, which is at the same time A will produce C. We want B is produced, but unfortunately C also is also produced in the second reaction. Complex is combination between 1 and 2. So as you can see here, A to forms B and C. A will react with C to form D. It is similar series and parallel. What we have to do in order to come up with this? So there is no specific solution for all cases. Hence, calculation and optimization in material energy balance is a must. For example, we need to optimize the ratio if we have more than one reactor. The size of the reactor must be optimized. For example, if you have series reaction like this, you must have correct size so that the concentration of P is maximum, and the heat effect must be right. For example, if we want to we have to analyze the energy balance so that we can decide whether the reactor is adiabatic or diabatic, isothermal or non-isothermal. So the heat effect must be correct so that it will not reduce the selectivity, yield, and conversion. The type of the reactor also will affect the selectivity, yield, and conversion. So we got to determine by using Levin sphere plot. This is a plot where we can check what type of the reactor can have more conversion and less smaller size. So the levels per plot is very important to improve or to get the right type of the reactor. Example of multiplications that I can show you as a case study. Assume that a reactor has the following reactions and the respective rate law is given. So A from B, and then in the same time A is involved in producing C, which is undesired. Assume that the first reaction is elementary, second reaction is non-elementary, which is the power of 2 or second order. If B is the desired product and C is undesired product, so selectivity of B is rate P per rate C equals to negative RA1 per negative RA2 equals to K1 CA and K1 Ka2 Ca square. Finally, we have this equation. By seeing this equation, you can see that Ca is denominator. So in mathematics, if you have this equation, so Ca is inversely proportional to S. It has opposite effect. If you decrease Ca, you will have high S. If you have high Ca, you will have lower S. So in order to have high selectivity, you must reduce the concentration of A at some level, not very low, some level. So you got to also include the cost effect. Second is you must make sure that the rate constant of Ka1 higher than Ka2. How do we have that? So K is K naught exponents of energy activation energy per R, and then RT naught per RT. Sometimes I use T naught, sometimes I use T1. As you can see here, when temperature increase, K increase. So when you plot a graph between K1 and K2, if let's say we have to look at the activation energy. The activation energy will determine whether the K very sensitive or not to the change of temperature. So if we plot a graph, if let's say EA1 is lower than EA2, activation energy for first reaction is lower than activation energy of the second reaction. When we calculate K versus T, it will be like this. K, so first reaction will not very sensitive to the temperature. So this is Ka1, and then this is Ka2, and this is offset, where Ka1 per Ka2 equals 1. So the Ka1 will be higher than Ka2, below than T set. As you can see here, Ka1 higher than Ka2 when temperature is lower than T set. T is lower than T set. Ka1 per Ka2 lower than higher than 1. Higher than 1. So this is this indicate that you must have low T lower than T set, so that the rate constant is high. Ka1 higher than Ka2. Ka1 is higher than Ka2. Then only your selectivity will be high. Okay, this is one example. You can have more. This is just an introduction and how we deal with problem of fraction in the reactor design. That's all. See you and Assalamu alaikum.